Okay, implicit differentiation. So to understand implicit differentiation, we first want to know what are implicit functions. So suppose we write a function in the format as y equals to f of x, then this is an implicit function. Sorry, this is an explicit function. This is called an explicit function because y is represented explicitly as some function of x. On the other hand, you have a a possibility of explaining some value k as a function g of x comma y. So, for example, xy equals to 10. So this is an implicit function. So a lot of time the same function can be represented as both an implicit and an explicit form, because if you can rewrite this function as y equals to 10 upon t. So this becomes the explicit form. Okay, so in explicit form, on one side you have y, on other side you have some function of x, but no presence of y. In implicit form, you have some combination of xy equals to something. Okay, so this is the difference between explicit and implicit form. For example, y equals to 10x square plus 3x minus 5. This is explicit. I write the same thing as y minus 10x square minus 3x minus 5 equals to 0. So this becomes implicit. So the general formula of implicit function is k equals to g of x comma y. So consider this particular function xy equals to 5. So I know that there exists some explicit form y equals to f of x. Some explicit form for this implicit function exists. I'm not interested in finding that explicit form. I want to be able to find the derivative without finding the explicit form, because sometimes finding the explicit form is difficult. Okay, so if I give you a function like x square, 3x square plus 10xy minus 7y square equals to 0, you cannot rationalize this as y equals to f of x easily. It's going to be a quadratic thing, so it's going to be complicated. So I'm saying that there is some y equals to f of x, which is the explicit form of this implicit function. So I replace this y with that f of x, and then I say x times f of x is equal to 5. Then I differentiate this entire thing with x with respect to x while applying the product rule. So when I apply the product rule, I get f of x plus x times f prime of x. This should be equal to 0. Right, so what I get is f prime of x is minus f of x by x, and finally for f of x, instead of f of x, I can write just the function y, because I know that f of x is nothing but y. So f prime of x becomes minus y by x, which is minus pi by x square. If I were to write y as here, I know that y is equals to 5 by x. If I'm required, I can write it like this. If I do not want, I can stop here. If I have x and y values, I can stop here. So generally what happens is they give me some function, for example, this explicit form, and they ask me the slope, that is basically derivative, at a particular point 2, 1. So I'm going to differentiate this entire thing. So while differentiating, you do not need to replace y with f of x and everything. You can keep y as y. So you can just differentiate, assuming this is some function y of x and x. So when I differentiate y cube, differentiation of y cube is going to be 3y square times y prime. Okay. So if you're getting confused, you can replace y with f of x. So this becomes f of x cube plus 3 times x square f of x. And then you can do, instead of writing f of x and then replacing with y, I'm saying a easier thing is just assume y is f of x, y is some function of x, and start differentiating. Now, when I'm saying that you assume y as some function of x, it automatically implies that y is not a constant with respect to x. Okay. So a lot of times you would get confused because sometimes what we say is when you differentiate with x, keep y constant. That is partial differentiation. This is not partial differentiation. I'm not saying to differentiate with respect to x, keeping y constant. I'm saying y itself is a function of x, so y cannot be held constant when x is changing. So that is not possible. So this differentiation becomes 3y squared times y prime, where y prime is f prime of x, plus when I differentiate this thing, this becomes 6xy plus 3x square y prime. This net thing should be 0. Okay, so I get this result, and then I can take y prime common. So I get y prime, so this thing equals to 0. Then I take y prime common, so I get y prime equals to this thing, which I can resolve as this. And then final step is you put 2 comma 1. So y prime at 2 comma 1, which is nothing but the slope at 2 comma 1, will be equals to minus 2 into 1 upon 2 square plus 1 square. So that is minus 4 by. So let's look at this example which I gave you and find this guy's derivative at uh, at 2 comma 1. Let it be 2 comma 1. What is going to be the derivative of this function at 2 comma 1? Hello. Are you guys saying anything? I am unable to hear you. It's not so difficult.
So I got minus 7 by 3.
Okay. All right, so let's check this thing. So differentiating this would be me 6 times x plus 10y plus 10x y prime minus 14y y prime is equals to 0. So this implies that y prime uh, must be y prime times 10x minus 14y is equals to negative of 6x plus 10y. So y prime must be equal to negative of 6x plus 10y divided by 10x minus 14y. So minus of 6x is 12, 12 plus 10 divided by 10 times 2 is 22 minus 40. So this is minus 22 by 8. So that's minus 11 by 4. Okay. Did I make any mistake or did you make a mistake?
Sir, won't it be 10 into 2, 20 instead of 22?
Yes. 20. So this becomes 6 minus 11 by 3. Is this correct?
Yes, sir. I've got same.
Okay, fine. So this is the value of y prime, which is basically dy by dx. Okay. Let us say that this function is g of xy. Now, what I've basically done is that I found dy by dx. Another thing that we use very often is del g by del x, right? So what is del g by del x? Del g by del x here is when I partially differentiate this g function with respect to x, keeping y constant. So del g by del x for this function is going to be 6x plus 10. So it depends on what the examiner is asking you. If the examiner asks you the slope of this particular thing, you have to rely on dy. You can rely on dy by dx. If he asks you the partial derivative, you can use del g by del x upon del g by del x. That will give you partial derivative. So it really depends on what are you interested in, and that's why you have to pay attention. So these things are going to be different. On a side note, del g by del x upon del g by del y will also give you the slope. So this is going to be 6x plus 10y. Sorry, it's going to give you negative of slope. So another way to find the slope is minus del g by del x upon del g by del y. So this thing will give you del g by del x is 6x plus 10y, del g by del y. When you differentiate with respect to y, it will give you 10x minus 14. So you compare this and this, they are same. Okay, if I put a negative sign here, they become the same. So you will again get minus 11 by 3. This is essentially what we studied in our economics part, in micro part. This is basically your MRS, and this is dy by dx. Sorry, MRS equals to minus MRS is equals to dy by dx. So it's the same, right? So you can use this alternate technique to find the slope also, that del g by del x upon del g by del y, or you can use implicit differentiation. Now, sometimes they might ask you a double derivative. So if you want to compute, let's say y double prime for the double derivative for xy equals to 5, then when I differentiate it once, what I get is y plus xy prime equals to 0. and then I differentiate this again. So when I differentiate again, I get y double prime plus x y double prime plus y prime is equals to 0. So this part will give me y double prime equals to minus of y prime by x. And this part will give me y prime equals to minus y by x. So I can substitute this value of y prime here, right? And I'll get the double derivative as 2y upon y prime y by x. Why am I getting 2y? Okay, yeah. So y prime plus y prime y double. Oh, okay. This is y prime. So y double prime is equals to minus 2. Negative of 2y prime by x. Where you again substitute this minus y by x, so you get 2y by x squared. So this becomes the final value of y double prime. So if they ask you, let's say somewhere, what is y double prime, the final result has to be in terms of y and x. You cannot leave it here. You cannot leave the final result in terms of y prime. You have to substitute this y prime here and get the final result in this format. So for this question, three x square plus 10xy minus 7y square is equals to 0. Find y double prime. Okay, so try doing it later on. It will take you some calculations. I want to move forward.
Sir, you are mute.
Can you please hear me? Hello.
Yes,
sir.
so we can hear you.
Okay. So the power went off momentarily and my router is down. So I'm running the things to my hotspot. So let me know if quality isn't good enough. And I'll change back to router in a couple of where was that? Yeah. So these are some examples of implicit differentiation which you can do on your own. Then another example of linear approximation of okay. Another example of using this is going to be linear approximations. So linear approximations are used to find approximate functional values, right? Find approximate functional value. For example, suppose I want to find square root of 4.02. Now I know that this is approximately equal to 2. So this will be 2 point something something. But what is this something something approximately equal to? So how can I get close to this something something? So that is going to be something we deal with in linear approximations. So suppose a function f is defined as f of x. Okay, so I know the functional value at a. Suppose I know f of a. This is known. And f of x is something that you have to find out. So you can use this approximation that f of x is approximately equal to f of a plus f prime of x minus. So how does that work out? So let's say this is any function. Let's suppose that this is some function f of x like this. And you know its functional value at a, at some point a. At some point a, you know its value. And another point x, you want to find its value. Now, if you know the slope of this function at, let's say, a, then I know that this value is going to be f of a plus, let's say, this distance is delta f. Oh, okay. I thought it was sorry. So I'll repeat. So linear approximations, I'm going to use this linear approximations to find approximate functional values. So suppose I know the functional value, I want to find functional value of root 4.0. So I know it's going to be 2 point something something. What is this something something is something I'm going to estimate using differentiation. So let's say f functional value at some point a is known to you, functional value at some point x is something you want to find. So let's consider this graph of f of x as this green curve. Okay, so assume that the green curve is f of x. You know its value at a. At a, you know its value is f of a. At x, you do not know what this f of x is. But using derivatives and slope, I can find this value. This value is basically if I were to construct a tangent here, if I were to construct a tangent line at this point a comma f of a to the curve, then its functional value at it will pass at x to the point f of a plus delta f, where this delta f is basically going to be equal to f prime at a times this distance, this horizontal distance, because that is the definition of slope. Okay, slope m is delta f upon, slope m is basically delta f upon x minus a, right? And slope is nothing but f prime at a. So this becomes delta f becomes f prime times x minus. So you can finally substitute this value here, and you can say that f of x is approximately equal to f of a plus f prime at a times x minus. Okay, so it's going to be approximately. So suppose I want to find cube root of 1.0. So the example is find cube root of 1.03. So I know that cube root of 1 is 1. So I'm going to use that particular thing. So my a becomes equal to 1. My x becomes something that I want to find 1.03. So first thing I know is f at a is basically cube root of 1, which is 1. Next thing is f prime at a is cube root of x. What is going to be the derivative of cube root of x? What is derivative of cube root of x? Anyone?
So x bar minus
What
2
is
by 3,
derivative?
x bar
X to
minus
power
2 by
minus
3
2
by 3.
by 3. Yeah. So 1 by 3 times x to power minus 2 by 3, which basically be equal to, for x equals to 1, this implies that this derivative will be equal to 1 by 3. So f prime at 1 is going to be 1 by 3. So now I can apply the formula that f of 1.03, that is f of x, equals to f of a plus f prime at a into 1.03 minus x minus a, 2x minus a. So that is going to give me f at 1 is 1 plus f prime at 1 is 1 by 3 times 1.03 minus 1 is 0.03. So this is 1 plus 0.01. So that is 1. So that's how linear approximations work. Let's move to single variable optimization. So now this is the main topic that we want to optimization. So we started optimization and we looked at extreme points, and I told you that a function f has a global maximum. Global maximum means the functional value at that maximum will be greater than equals to functional value everywhere else. And a local maximum is where functional value is highest at a local maximum compared to other regions. And similar concepts apply to local and global minimums. So if you have a function which looks like this, yeah. So suppose we have a function which looks like this. Oh, everything that can go wrong is going. We had internet issues, we have server issues. Now I have some issue with my laptop as well. Okay, so let's say you have a function like this. So I know that this is a local minima. This is a global slash local minima. Okay, and this is a global slash local maxima, whereas these two are just local maxima. So the first definition that we looked at is that an interior point is C such that f is not differentiable at C or f prime C is 0 is called a critical point. So what are critical points? Critical points are such that f prime is equals to 0 or f prime does not exist at that point. So those points are going to be your critical points. Okay, so we are going to look at f prime function and basically try to find what are the critical points. So sometimes it will be very apparent to you by looking at the nature of the function. Sometimes you'll have maybe do some algebra before you are able to find. So this theorem, basically there's a theorem which says that the maxima or minima of function on A are going to be restricted to the following points: the boundary points and the critical points. And critical points by themselves are points where f prime does not exist and points where f prime is 0. Okay. Boundary points, I know what boundary points are. These come from the domain of the function. They are dependent on the domain of the function. So suppose you have a function. For example, you have a function f defined from -2 to 2 such that f of x equals to modulus of x. So my first question is, what are boundary points? What are the boundary points of this function? What are the boundary points of this function? Remember, for boundary points, you don't need the function. You just need to look at the domain of the function. What are the boundary points of the function? Come on, it's not so difficult. What are the boundary points of the function?
So minus 2 comma 2 and 2 comma 2.
Wait, how do you write it? -2 comma 2. No, I'm only interested in x values.
Okay. Then
Only
minus
x.
2 and 2.
Yeah, -2 and 2. Okay, I'm not interested in y values. I'm only interested in x, only the domain. Okay, so -2 and 2 are the boundary points. Question number 2 is f prime equals to 0. Sorry, f prime does not exist. What are the points at which the slope of this function does not exist on this domain?
Set 0.
0. Yeah. Are you able to follow why 0 f prime does not exist? Others who are not answering, if you have a doubt, you need to ask. F prime equals to 0. What are the points at which f prime would be 0 for this function? What are the points at which f prime does not equals to 0? Come on.
So it doesn't exist.
Very well said. So this says that the search for maxima or minima should be limited to boundary points and critical points. So the only points you need to consider is -2 to 2, -2, 0, and 2. So only these points will give you maxima, minima, and nothing. Okay, so everything is going to be these points. Okay, so after this, one thing is definitely what you can do is you can check values. Functional value at -2 is 2, functional value at 0 is 0, and functional value at 2 is also 2. So I know these two are the maxima, this is the minima. So once I have narrowed down on the boundary points and critical points, after that, one easiest way is just to substitute all the values and check. Okay. maxima and minima will exist. So that's why I'm sure that because maxima minima exist in this particular function, so going to be there. It is not that there's no maxima, no minimum. For some more complicated functions, the analysis would again be much more complicated. So in this example, example 8.3, okay, how do I get f prime does not exist, by the way? So in a function which involves a modulus, you have to write the functional form. F of x equals to x if x is belonging to 0 to 2, closed 0 to 2, and it's going to be minus x if x belongs to minus 2 to 0. So once you define it like this, I know that this part is completely differentiable. This part is completely differentiable. Only point where it could have a non-differentiable part is at 0. So if f prime does not exist somewhere, then that point is 0. If at all there is such a point where f prime does not exist, then that point has to be 0. So the only point you need to check is 0. So how do I check at 0? So f prime at 0 plus, okay, f prime at 0 plus is going to be the derivative of this thing is 1, and f prime at 0 minus is equals to the derivative of this part, which is minus 1. Now f prime is nothing but a limit, so I'm saying the right hand limit of this derivative is 1 and the left hand limit of this derivative is minus 1. So the right hand and the left hand limits are different, so that's why I say that this limit, which is basically the derivative, it does not exist. So you'll have to do this sort of when you have a piecewise function where it may exist, where it may not exist. You have to check it manually. If it exists, then you can't do anything. If it exists, then don't include it in your structure points. Only when f prime does not exist or when it is 0, it's only then that they get included into your set of critical points. Also, points of discontinuity automatically by that logic, they get included in set of critical points, because if the function is not continuous, then the derivative also does not exist. So derivative is a more stricter condition than continuity. All right, so if you have this function f of x equals to x from minus 1 to 0 and then 2x, so this function looks like this. Here it will look like this, here it will look like this. So first of all, the critical points, what are the boundary points? So I know the entire set is minus 1 to 0 or minus 1 to 1. So the boundary points are minus 1 and 1. Okay, so then critical points, this part prime is smooth, it is 1 everywhere, so no problem. In this part, it is 2 everywhere, no problem. The only problem which can happen is at 0. So I know that left saying my connection is unstable. If it happens once more when I go offline, I'm just ending it. I mean, we at some point you have to listen to God. Just give it. Can you guys hear me?
Yes, sir.
Yes,
Sorry
sir.
for asking this again and again. Or something or keeps coming up. Anyway, so I know the left-hand limit of the derivative f prime for 0 minus is 1. And from here, I know that f prime at 0 plus is 2. So 1 is not equal to 2. So the limit will not exist. Limit meaning f prime does not exist. So 0 is also a critical point. So minus 1, 1 and 0, these are your critical points. Then you can just substitute the values and see which of them is giving the one which is giving the highest value is going to be the maximum. The one which is going the minimum value is going to be the minimum. But here you'll see that at minus 1, the functional value is minus 1. At 1, the functional value is 2. At 0, the functional value is 0. So here I cannot be sure that which is what. Because 0 could be a local minimum. It's definitely not a local or sorry, not a global maxima or minimum. That is clear. Because minus 1 is your global maxima, global minima. Minus 2 is your global maxima. What about 0? What is 0? Is it globe? Is it a local minima? Is it a local maxima? Is it nothing? What's happening? I cannot be sure. So I need some more information here about 0. So one best way is to look at the f prime values at 0, around 0. So to the right of 0 function is increasing, to the left of 0 function is also increasing. So if it is increasing on both sides, it means that 0 can neither be a maxima nor a minimum, which is amply clear from the graph of this function. Right? If you look at the graph of this function, it will look like this. So I know that f of 0 is 0. Any point to its right, f of 0 plus will be greater than 0, which implies that 0 is not a local maxima. Any point to its right gives a higher value. Similarly, any point to its left of 0, f of 0 prime is negative, which implies 0 is not a local minimum. Now it's obviously clear from the graph here that 0 is neither a maxima nor a minimum. But the idea that I am trying to generate here is something which helps us in questions which are more complicated than just this one. For example, let's consider x cube on some domain. F of x equals to x cube on the domain minus 1 to 1. Okay. So first of all, what are boundary points? Let me ask this question to Yuvakshi. What are going to be the boundary points?
Sir, minus 1 and 1.
Very good. Minus 1 and 1. Okay. Next question to Kanishka. F prime does not exist. What are the points at which f prime does not exist for this one?
Sir, at 0.
What is the functional value of f prime?
3x square.
Okay, so what this 3x square, does it give you any reason for not existing at any point? What is the value of f prime at 0?
0.
But 0 exists. 0 is not existing. 0 exists. 0 is not existence. Not existence is this one. That here the slope is 2, here the slope is 1. So here it does not exist. This is not slope 0. I'm not saying this here slope is 0. 0 and not existing is not the same thing. So I'm going to ask you again, f prime does not exist. Where does it not exist?
So it exists everywhere in the domain.
Very good. So f prime not exist is nonsense. Next question to Kashish. F prime equals to 0. This is my f prime. When does it become equal to 0? Kashish?
So when x will be 0.
X equals to 0. Very good. Okay. So basically, my critical points are going to be union of these three sets. The union of these three sets are -1, 0, and 1. Now I can write the functional values at all these points. At -1, it is -1. At 0, it is 0. At 1, it is 1. So this becomes your global maximum. This becomes your global minimum. What happens at 0? That is the question. That what happens at 0? So to see the story at 0, without drawing the graph, okay, by drawing the graph it will be amply clear. I want to look at what happens to 0 at without drawing the graph. So I know that f of 0 is equals to 0 and f prime is 3x squared. So f prime at 0 plus is basically f prime at some value f prime at some value h positive, which is basically 3 times of h square. So this is positive. So to the right of 0, function is increasing. To the left of 0, this function, whatever negative h, to represent minus, I'm writing this as negative h. So this square ensures that this thing will still be positive. So the function is increasing to the left of 0 and it is increasing to the right of 0. So whatever is the story at 0, the functional value, the function is going to be increasing here and increasing here. So it's going to be an increasing function passing through 0, 0. Because functional value at 0 is 0, so I'm writing this as 0, 0. So the function is increasing. So any value to its right will have f at h greater than 0, and any value to its left will have f at h less than 0, less than 0. So 0 is neither a maximum nor a minimum. So this implies that 0 is neither a maximum nor a minimum. Neither a local maximum nor a local. In fact, in time we'll come to define such points. I know that f prime at 0 is 0. So it still counts as a critical point, but it's not an increase. The function is not achieving anything here. So this will, in fact, in time come to be known as an inflection point. So you see what an inflection point is. Not all such points are. The definition of inflection point itself is a little complicated. So we'll handle that when we reach there. But first, we want some general rules to be able to identify my optimas. So first, we define the necessary first order conditions. So what are the necessary first order conditions? So the first order necessary condition is that says that if a function is differentiable in some interval I and sees an interior point, then for x equals to c to be a maximum or a minimum point for f in that interval, a necessary condition is that it is a stationary point of f. That is, x equals to c satisfies the equation that f prime of x is equals to 0. So at that point, the derivative must be 0. if you are looking at an interior point, then for it to be a maxima or a minima, it should have f prime. Now, why am I calling it a necessary condition? Necessary means this needs to be true, but it being true does not imply that the function will have that point as a maxima or a minima. So suppose for a particular function, this set is all the points where f prime is equals to 0. This set of points is the set of all points where f prime is equals to 0. Okay. And this will be the set of points at which you have either a maxima or a minima. So there are going to be points like this one where f prime is 0, yet neither max nor min. So there are going to be points like we just saw in x cube case, x equals to 0 is a point which satisfies this condition, yet it is not a maximum or a minimum. So that's why it's a necessary condition which you have to satisfy, but that is not guarantee that you will be a maximum or a minimum. Okay, so it's like a necessary but not sufficient criteria. For example, a necessary criteria for DSC is you should have 60% in your graduation. Okay, now just because you have 60% in your graduation does not mean that you will become eligible for a seat, that you'll get a seat. Okay, but one thing is certain, that if you do not have 60%, then you will not have a seat, which means that any point here cannot be a maxima or minima. Remember, we are talking about interior points where the function is differentiable and all those things. We are not talking about boundary points and anything. You can have a boundary point which does not satisfy this condition and yet be a maxima or a minima. I'm talking about interior points only right now. So an interior point cannot be a maxima or minima if its f prime is not 0. So for a differentiable function and an interior point strictly. Now I'm stressing this much on this particular point because they ask questions based on what do you mean by necessary? What do you mean by sufficient? Okay. So next thing is, what is the sufficiency? Okay, we'll come to the sufficiency condition in a bit. First, we look at some cases. In many cases, we can find maximum or minimum values for a function just by studying the sign of its first derivative. So f prime greater than equals to 0 for x less than equals to c, and f prime less than equals to for x greater than equals to c, then it's a maximum point. So we are saying that at some point c in the history of a function, at some point c, so for the first example, consider this point c. So to all points to the left of c, the function is increasing. So the function is increasing here, and to all points greater than equals to c, so this should have been c. This is the typo. To all points to the right of c, the function is decreasing. So it is decreasing. So if you even know this much, you can be certain that the point c is a local maximum. To the left of this function, the function must be increasing. To the right, it should be dipping down. So then it becomes a local maximum. The converse thing is true here. The second thing, it will be represented by a graph like this. Here the function is decreasing. Here the function is increasing. So you have decreasing to the left of c and increasing to the right of c. Then it's a minimum. So this becomes a local minimum. Okay. All right. So let's do an example. Consider this function, which is given by this, which you can factorize in this format. find all zeros of f of x. Zeros means where f of x becomes equal to 0, and find f prime of x. And second part is interval where it increases, decreases, and third is this. So let's work on this. First part, what are the zeros of this function? At what x will this function become 0?
So 0 and log 4.
Very good. So e of x minus 1, this part becomes 0 at e to power x equals to 1, or x equals to log 1, which is basically 0. And this part becomes 0 at e to the power x equal to 4, or x equals to log 4. So 0 and log 4. So these are the zeros. What is going to be the f prime of this function, the derivative of this function? Where's the function? Oh, so what is the derivative of this function, f prime?
So twice of e2x minus 5ex.
Yeah. So you can derive this thing. So differentiation of this will be twice e to the power 2x. Differentiation of this thing is minus 5 e to the power x. E to the power x, the differentiation is e to the power x. So if you remember that one, that this thing is very easy. Now that you have f prime, tell me where is f prime positive? This is basically f prime positive. And where is f prime negative? Let me ask this question to you, Akshi. F prime positive. Where is f prime going to be positive? So, sorry, I'm trying to say something. I can't hear you. Yuvakshi, are you with us? Kanishka already has helped us with f prime equals to e twice e to power 2x minus 5 e to power x. Okay, so she's not present. So Kashish, can you tell me where is this f prime being 0? Sorry, f prime being positive. Kashish, can you hear me?
Yes, I'm trying.
Okay. Can you take something common here, Kashish?
E to the power x.
Okay, so when you take e to power x common, what do you get?
2 e to the power sorry, x
Yeah, very good, very good. Minus
5.
right. Okay, so I'm saying when is this part positive? First of all, e to power x. E to the power x is always positive, right? Because it cannot be negative. E is a positive number. E is a positive number, which is like roughly 2.303 something. A positive number to any exponent is always positive. We actually did in the first lectures, we did some graphs on exponential logarithmic functions. So this was the graph of e to the power x. At 0, it became 1. If you put x equals to 0, this becomes e to the power 0, which is 1. But it is always positive. That is the essential thing. So the left side is always positive. So the entire thing to be positive, I just need this thing to be positive, right? So what do I need for this thing to be positive?
X is greater than log 2.5.
Yeah, I was asking the question, but yeah, I mean, this just becomes e to power x greater than 5. So e to power x greater than 5 by 2. So then you can just take log, so x greater than log of 5 by 2, which is x greater than log of 5. So f prime is increasing. So this is increasing, or f prime is positive for x greater than log 5 by 2, and it is decreasing for x less than log 5 by 2. Right? So that solves the second part. So the possible extreme points is going to be log 5 by. This is the only possible point. Plus, I see that at log 5 by 2 to the left, for x less than log 5 by 2, my function is decreasing. To the right, it is increasing. So what will be log 5 by 2? Will it be a maxima or a minima?
So minima.
Minima, very good. So it will look like this, decreasing here and then increasing. So it's going to be a minima. And there is no other point. So it's going to be a single point to the left, it's going to be decreasing, to the right, it's going to be increasing. Right? All right, next they ask us to find limit x tending to negative infinity f of x. So yeah, sorry, where is this? Here is the function. X tending to negative infinity f of x. So I know that at negative infinity, this thing becomes 0. This thing becomes 0. So the entire thing just becomes 4. Right? So this thing is 4. So the graph of this function can be plotted just by this information that at log 2.5, you get a minima. Here the function is decreasing and here it's increasing. And when it's at negative infinity, it will become equal to 4. Okay, as you go towards negative infinity, the functional value will go towards 4. So this much information is sufficient to plot the graph of this function. Also, I sometimes need x tending to positive infinity. So here I know that limit x tending to positive infinity is going to be infinite, because e to the power 2x is going to dominate this e to power x. Right? So because it has a higher power. So limit x tending to positive infinity f of x will be equal to infinity. So that's why at negative infinity, it tends towards a finite value 4, whereas at positive infinity, it will keep on increasing like this. So that's the entire graph of this particular function. Okay, I have one more function here, e to the power x minus 1. Why do I have this one more function here? Anyway, so asymptote brings me to an important topic on asymptotes, on which there's another PDF which is uploaded here, which I want you guys to go through. So asymptotes are something that, so sometimes what happens is the graph of a function becomes similar to a straight line at infinities. Okay, at infinities, the graph, or at some finite values also, the graph of a function becomes similar to a line. So for example, this is the graph of this function 3x plus 1 upon x square minus 4. So you see at negative infinity, it is going to be grazing along the x-axis from below. At positive infinity, it will graze along the x-axis from above. Similarly, to the left of -2, it's going to go down to along the line x equals to -2. To the right of -2, it's going to graze along this line along x equals to -2. So this dotted line, these are vertical asymptotes of this particular function, and the x-axis is a horizontal asymptote of this function. Now, asymptotes are not strictly speaking in the syllabus. I have never encountered any question in the past years regarding asymptotes. So I want you guys, I have given this document, you can go through it. If you have doubt, you ping me. I'll take an extra session on Wednesday and get done with asymptotes. It will take hardly 45 minutes for me to do it, but I would ideally want you to have a go at it first. If you can understand it on your own, then great. If not, then we can discuss. Okay, so do this asymptotes file. And if you have doubts, let me know by Tuesday so that we can cover it on Wednesday. All right, so here I did not need anything in this example. I did not need anything other than f prime values to find my optima. I just needed my f prime. Give me f prime, I'm done. But that is not always true. Sometimes f prime is insufficient. So we want to introduce concavity and convexity here. So extreme points for concave and convex functions. So suppose that f is concave with f double prime negative. A concave function looks like this, right? This is the graph of a concave function. Then f prime is decreasing in I. So if f prime is 0 at an interior point, so this is a concave function. So suppose at some point C you have f prime at C 0. Then what must be true here is a concave function is f double prime reducing. So f prime value is 0 here. So it must keep reducing to the right of C. So to the right, I should have f prime less than 0. And to the left, I should have f prime positive. So this function is increasing here and decreasing here, which means that for a concave function, if you have a stationary point like C, then this should be a point of maxima. So these two conditions together imply that C is a local maximum. Okay, so if you just have these two conditions that f prime is negative and C f double prime is negative at C and f prime at C is 0, then C must be a local maximum. The converse condition holds true for minima. So the idea is that f prime negative and f double prime negative and f prime 0 implies local maxima, and f double prime positive plus f prime 0 implies local minimum. Now I'm not just giving you the rules, I'm drawing graphs here because it is easier to remember things using graphs. So a lot of times you might get confused in exam. I know that I did get confused with these things for the longest time. So when I would get confused, I'll draw graphs and verify, okay, what happens, concave hai or ye hai, okay, it looks like a maximum. If I draw a concave function, this is my stationary point, yeah, it's a maximum. Okay, so that's how you can maybe remember it. So a concave function, slope is reducing, it is positive, then 0, then negative. So concave means f double prime is reducing, f prime is reducing, so f double prime must be negative. So f double prime negative, f prime 0 means local maximum. So that's how you can do it, maybe with the help of some visualizations. So I'm just telling you things that help me. Maybe you are good at remembering, so you might not need it altogether. That would be too great. If you can't remember it, then maybe you remember this graph and they will come to your aid. So the second derivative test is it says that if f is a twice differentiable function on interval I and C is an interior point, then f prime 0 and f double prime negative implies strict local maximum, and f prime 0 and f double prime positive means strict local minimum. So this is just the second derivative test. Now finally we reach inflection points. So inflection points mean that inflection points. So we defined a twice differentiable function. Twice differentiable means f prime and f double prime both exist. To be concave or convex. Okay, so the bracket gives the alternate definition. So we'll ignore the bracket for now. So we have a twice differentiable function that is concave in an interval I, and f double prime is negative, less than equals to 0 for all x in this interval. So points at which the function changes from being convex to concave or vice versa are called inflection points. Okay. So inflection points are points where the function changes its nature from concave to convex. A function need not be concave forever. You can define a function like this. Okay, so in this region, the function is concave. How do I know that? I connect any line segment here, it always lies below the graph. So this part is concave. Whereas this part is convex. Because I connect any line segment, it lies above the curve. So this part is convex. So at some point here, the graph changed its nature from concave to convex. This point is called as point. This point is called as point of inflection. I don't know if you have heard this thing in the news, but when COVID cases are discussed, mathematicians look for point of inflection. Why do they look for point of inflection? So if you look at a typical COVID curve, let's say, let me open the browser and show you why inflection points are important. What was that website? What does it do? Yeah, I don't know if you have been on this website. It's a very nice website to get data about COVID cases. So if you look at, let's say, the data for India, is India. So it's fine. Yeah. So you see here the graph is convex and then it starts becoming concave. So at some point here, the cases, you reach the inflection point in your cases. Again, you see here the graph is convex, but here it is definitely concave. Right? So at some point here, you reach the point of inflection. Why is point of inflection important? Because at point of inflection, now inflection point has reached. So the f prime is not increasing anymore. What is f prime of cases? If this is the case, a total cases thing, f prime is rate of change of total cases, that is daily new cases. So an inflection point is reached when instead of increasing, f prime starts reducing. So the new cases are now lower than previous days new cases. So you know that once you've reached an inflection point, then cases will start dipping and maybe you'll reach the curve will flatten. So they keep saying flatten the curve, flatten the curve. So that's what they mean. First, you have to reach the inflection point. At the positions where it is convex, you are at the beginning of the wave. Then it gets concave. That's when you are flattening the curve. Okay, so that's the idea of flattening the curve. So these are the two waves in India. So as you can see, again, this part is convex, and then you get concave part, and then we have almost reached the flat part right now at 40,000 something. So this is basically the idea of inflection point. So how do you identify inflection points?
So, sir, the point of inflection basically marks the rate of change in the slope of the curve. Change in the rate of, sorry, the rate of change in the slope.
Rate of change in the slope. Yeah. So it's when the rate of change of the slope, basically the slope has stopped increasing or decreasing. So in this case, we are interested in such inflection point where the rate of change has stopped increasing. So the previous day's cases are higher than this day's cases, today's cases. So once inflection point is reached, you can take some sign of relief that at least daily cases are not increasing anymore. So, so inflection point is when f double prime changes its sign. The inflection point is, in a nutshell, inflection point is when f double prime changes its sign. So let's do two very interesting examples. Example 1, f of x equals to x cubed. So f prime of x is 3x squared and f double prime of x is equals to 6x. All right. So I'm saying inflection point is where f double prime goes from positive to negative. So obviously at inflection point, f double prime must be 0. So here I get that x equals to 0 could be an inflection point. Why am I writing could be? Because it's not necessary that if f prime 0, then it's an inflection point. Why will become clearer when I reach the next example. But here, how do I check for certain if f double prime is an inflection point? So for that, you need to check f double prime at 0 minus and f double prime at 0 plus. So they should be of opposite signs. So I know that f double prime at 0 minus is 6 times x, so that's going to be negative, and f double prime at 0 plus, since x is positive, this will be positive. So f double prime is changing its symbol around 0, so that's why x equals to 0 is an inflection. But let's do another example, f of x equals to x to power 4. So for this case, I know that f prime will be equal to 4x cubed and f double prime will be equal to 12x squared, which is 0 at x equals to 0. So now the question becomes, is x equals to 0 an inflection point or not? So for that, I'll need to analyze f double prime 0 minus and f double prime 0 plus. What is going to be f double prime 0 minus? Will it be positive or negative?
Positive,
And what will be f double prime 0 plus?
positive.
Yeah, because it's a square, right? Extra square. So the square gets rid of the negative. So you'll have it positive everywhere. So f double prime is not changing its sign around 0. So the curve is always convex actually. It's never becoming concave then convex or vice versa. It is convex here, it is convex here. So it is convex throughout. So this is not an inflection point. In fact, if I draw the two curves, this will become amply clear to you. So this is the graph for x cube. So it's convex here, sorry, concave here, and it is convex. Whereas the graph for x to power 4 looks like this, and it is convex everywhere. So x to power 4 ke liye this point is not an inflection point. So a lot of people try to remember inflection point as a point where f double prime is 0. And examiners exploit that. They will deliberately give you a function where you will end up at finding f double prime as 0, and then you will give the wrong answer. Okay, so don't remember f double prime as that. Remember that it is f double prime changing its sign. Not just 0, but it should go from positive to negative or vice versa. So that is an inflection. So if the point is an inflection point, it is not a maxima or minima. So this point is neither maxima or nor minima. Whereas this point, as you can see, is a minima. So if it is an inflection point, it cannot be a maxima or minima. And if it is not an inflection point, then it will be a maxima. So these two cases are always complementary to each other. Either you'll have an optima or you'll have an inflection point. Okay, so for an interior point, the steps go like this. Step 1, find f prime equals to 0. Okay, so assuming the function is differentiable everywhere and there's no so the best way that the examiners give this function is define a function going from R to R. So since the domain is R, there is no boundary point. And then they say that function, which is twice differentiable, which is twice differentiable. So they basically established that f prime exists everywhere. It is not, so you do not have any f not does not exist kind of situation. Plus f double prime is also existing everywhere. So they will give you this exact line. You'll find it. At least one question will have this exact line in every exam every year. So after that, if you want to find the optima, the step 1 is find f prime 0. So suppose you get some point C here. Second step would be check f double prime at C. If it is positive, then you have a minima. If it is negative, then you have a maximum. If it is 0, then it's not automatically an inflection point. This is the point I'm trying to make. So the step 3 is f prime at C is 0. F double prime at C is also 0. So check if it is inflection point. So in this case, you can get 3 cases, that f double prime C plus into f double prime C minus is negative, which is basically to the left and to the right, f double prime is changing its value. So this becomes an inflection point. Second case is f double prime C plus is positive and f double prime C minus is also positive. So in this case, the curve is convex and C is a minima. And third is f double prime C plus is negative and f double prime C minus is also negative. So in this case, you get C is maximum. Okay, so these are going to be your steps. Step 1, step 2, step 3. Obviously, if there are boundary points, then you will have to check boundary points also. If there are points where f prime does not exist, you have to check those points as well. Okay, so with that, I would like to end this lecture. We have mean value theorem, L'Hopital rule. Okay, I wanted to do this, but I have another meeting at 6, so I leave it at this. and I'll have to rush to another meeting. We'll schedule a lecture and I'll complete all this in the week. Okay, so I'll ping on the chat. I'll see you guys now. I'll say tomorrow for the micro lecture. I'm ending the class in a hurry. So if there are any doubts, you can ask me later. Okay, bye guys.
Thank you, sir.
Sure. Welcome.
Thank you, sir.
Thank you, sir.
Thank you, sir.